Oh, my iPad. Nuts. All right. So we left off with, I think, dot product. And we did projections. We did all this cool stuff. We're going to do more cool stuff. So here's a warm up. Think about it, and then I'm going to have you guys just chat with your classmates. So it says, for any two vectors, V and W, there always exists a third vector that is orthogonal to both V and U. Sorry, V and W. I want you guys to think about it, and then I want you guys to just decide, do you agree or disagree with the statement? So for any two vectors, any two vectors that, let's say it's in R3, that exist in R3, there will always be a third vector that will be orthogonal to both of them. Okay? So just think about it. See if you convince yourself, do you feel that's true? Then you agree. Maybe you think that it might not be true in some cases, then you disagree. Just think about it. See activity, folks. So I'll have you guys here to me in the chat until the class with your class. Actually, can you join me? I'll have you guys as well. And then I'll have you four here, okay? And then you four here. I'll call you guys.
Yeah, two vectors here. One here. What else? Yeah, but.
Yeah, let's do like
four here. This, right?
Three here.
Plus it's like.
All right, so do a quick check-in with your group. You want to maybe draw some pictures, whatever you guys want to do. Yeah. Well, I think, I guess it's one sorry.
Yeah. But I was gonna like have
Okay, convince me to the contrary.
You gotta convince me, because I don't know.
Okay, I understand what you're saying.
Yeah.
Any two vectors stick together, and then at this point here is where he's talking about, where then, no matter how these are oriented, at this point here, you can run a vector through it that would be more fun.
Okay, guys, just give me a feel. Let's see. Someone in this row. Agree, disagree? Who disagreed in this row? Who agreed? Okay. Can I have one of you guys share maybe what you agreed? Yeah.
I said, I originally this, but I changed my mind because
Hold on, guys. Just hold on. If I can hear it. Go for it.
if there's two vectors, there's always like a third axis where the vector would be.
So I see you're going like that. You're putting like the two vectors of that, right?
Yeah.
Okay.
axis. Or then if they're like that, there's a third one that that would go this way, and it would be technically the same vector because it had the same different direction.
Gotcha. Okay.
So it'd be the same.
Okay, cool. So then you said you originally disagreed, but then you changed to agree. Yeah. Okay. All right. Anybody on the disagree side? Can maybe tell us why you disagree. Does that mean most of you guys are agreeing? Okay. All right. So let's see. Okay, perfect. Does anyone have a question about it? Maybe a clarification?
Yes, and I see what project as well, because that would, like, it's a to be and I'm talking about
It would mean that if you take, remember, what did it mean for a vector to be orthogonal to a different vector? Visually, that's what that means, right? Yeah, so it's like it's perpendicular to both V and it's perpendicular to W. Right? But what was the actual definition of orthogonal? Okay, remember? That's again visual though, but the definition wasn't a visual definition. It had to do, like someone said,
dot product is 0.
it had to do with dot product, remember? So yeah, so there's some mysterious vector that if you took the dot product of this, what did it have to equal? It has to equal 0, and if you took the dot product of this, it's also has to equal 0. By definition, that's what that part meant. But then we also proved some properties that visually it also meant that it was 90 degrees, so it was perpendicular, right? Okay, so let's see. So visually, we are kind of seeing that at least most of you guys are agreeing that there should be some third vector that's perpendicular to these two. And so that's exactly how this section is going to start. So section 12.4, what we're going to call the cross product. Starts kind of like with a motivation, because the definition is really complicated. Very detailed, sorry, not too much complicated, but it's very detailed. So let me motivate what a cross product is going to be. And it's exactly what this warm-up is saying, okay? So say we have vectors, and let's give it components, V that has components V1, V2, V3, and W that has components W1, W2, W3. And we wish to find a third vector. We're going to call that one U, that has components U1, U2, and U3. That is orthogonal to both V and U. And so from what you guys discussed, your intuition says that there should be a third vector. So the goal is, if there is such a vector, then let's see what the components of that would be. So that we guarantee it's orthogonal to both. Okay? And so we're gonna start by just going off of the definition. Since this U vector is orthogonal to both of those, we have that U, or let me start with V first, that V dot U is going to be 0, and we also have that W dot U. That's just the definition of what it meant for this guy to be orthogonal. But now notice that when we take the dot product from what we learned yesterday, how do we do that with these two vectors? What is it that you were doing on Tuesday?
Multiply the corresponding components in that.
That's right. We just multiply the corresponding components. So this is the same thing as multiplying V1 with U1 and multiplying V2 with U2, adding those, and then V3, U3. And we're saying that's supposed to equal 0 because we want it to be orthogonal. And then the same thing with W. W1, U1, plus W2, U2, plus W3, U3. So, if we have these two vectors, V and W, we will actually know the components, right? Like, let's say this is 1, 2, 3, and this is like 3, 5, 6. We will actually have the components. What we wish to find are U1, U2, U3. Those will be unknown, but these will be known. Those will be given, right? So if I look at these equations, the V's and the W's will be known. So what are the unknowns in this equation? The U's, right? So notice that what we produced is we produced a system of equations where the unknowns are U1, U2, and U3. Okay? So this produced a system of equations with unknowns U1, U2, and U3. I'm not going to write the solution to it because it's going to take up like half of the board. But the textbook has the way it has all the algebra work there. Okay. But what the textbook will do is they will solve the system so that they can find what U should equal, what U2 should equal, and what U3 should equal. A whole bunch of substitution and elimination and all that stuff that you guys have learned with systems of equations. And once you find what U1 and U2 and U3 are, then you've found the U vector. Okay? That U vector, that result is what we're going to call the cross product of V and W. That's how it's defined. Okay? So you solve this guy here, and then that's going to give rise to this definition. So let me just add textbook solves U1, U2, and U3. They solve that. Through hello algebra. So that result is what we're going to call the cross product. So we're going to say for vectors V and W, the cross product, you're going to see it's very different from dot product. The cross product is defined to be V, and this time we use the cross multiplication symbol, so that when you go ahead and compute the cross product, we're going to get a mu vector which is gonna be this u vector, okay? We're gonna get this new vector u that is gonna have components. The u component, the first one that you solve for here, is gonna end up being B2 times W3, so the second of V and then a third of W, minus V3 W2. That is the U1 that is solved for in this system. And then the middle component, the second one, is V3W1 minus V1W3. It looks very random, but I'm going to show you guys something later. And organize it a little bit better. And then the third component, the U3 one here that gets solved for, turns out to equal V1W2 minus V2W1. A lot more to memorize than the dot product. So that's what the cross product is, okay? You multiply two vectors in this manner and you produce a third vector. That third vector is this one. That is going to be orthogonal to those two. And so let me draw a little picture here. So you got U right here. Oh, sorry. You got V right here. And Eleni, right? And as Eleni said, you put the initial points together. So then you put the other one here, W. And then what's going to get resulted from this cross product is a third vector, which we're calling V cross W. That's going to be orthogonal. So it's going to be perpendicular to V, and it's going to be perpendicular to W. Exactly what was said. So it's kind of visually what we end up with. Yep.
I remember both vectors here that we were in this.
So remember that if I pick a vector that's randomly floating in space, there are an infinite number of vectors. Remember, and on GeoGebra, I was looking at vectors that were just moving. It doesn't matter where they're positioned. All that matters is that they point in the same direction and they have the same magnitude. That's what made them different. So let's say I pick two random vectors that are not next to each other, right? Well, there is a vector that starts right here that is equal to this green vector. Yeah, so think of it as like I'm just moving it so that it goes like that.
So even for actual vectors, you can just.
You can pick two equal vectors that are next to each other to visually see that. That's a good point. So that's going to happen a lot in this class. Like, I can pick two random vectors that are here, but then when we're doing all this computational stuff, then we're looking at two equal vectors that are right next to each other. Okay? Because this is pointing in the same direction as this one, and this one's pointing in the same direction as this one. So if this is orthogonal to this one, then the cross product is also orthogonal to the one that's located over here, since it has the same direction. Right? Let's look at an actual example real quick. So let's say let's let V equal the vector 1, 3, 4, and W equal the vector 1, 1, 1. Therefore, if we try to find the cross product vector, you just have to be careful with what you multiply. We have that, I'm going to prepare you for something we're going to look at in a little bit. You see how we're gonna compute the first component? You guys see that? We're about to do the first component. So if I put V right above W and I ignore the first components, notice that what ends up happening is I have 3 times 1, which is V2 times W3, minus V3 times W2. So it's like this kind of crossing action that's happening. That produced this right here. Okay? So we got 3 times 1. So 3 times 1 is 3, minus 4 times 1, which is V3 times W2, which is 4. And then for the second component, now I ignore this, the middle one, the second one here. And then I got V3 W1. So again, I have like this cross, minus V1 W3. Okay? And then I got 4 times 1 minus 1 times 1. That's 4 minus 1. And then for the third component, I cover the third one, and now I have V1 times W2. So again, at this cross minus this cross. So it's 1 times 1 minus 3 times 1. Okay? Hopefully, slowly, you'll see the patterns with the cross product. So then, therefore, I'm going to get, what is that? -1, is that 3? Minus 2. And then you can confirm it, that it actually is orthogonal to both of these. I won't do it, but you guys could confirm it on your own. Take the dot product of this with this, it should give you 0. Take the dot product with this and this, and it should also give you 0. Okay? And so I'll just say, I'm not going to do it, but I'll just say, no, that if you take the dot product of this new vector with V, it'll give you 0. And if you do it with W, it'll also give you 0. And I know it's weird, the definition's funky. But it is produced from this whole process of solving the system right here. Okay. Now the question is, if I have 2 vectors and I find the cross product, is the cross product pointing this way or is it pointing this way? Because both of those are orthogonal. They're both perpendicular, right? To both of those vectors. So which way is it going? So we're going to use, again, the famous right-hand rule that I was showing you guys last week. So some comments about this cross-product business. So the first one is you use the right-hand rule, and I'll review what that is again, to decide the direction of V cross W. So in general, you have some left vector. You have some left vector that's on this side cross a right vector, the one that's on the right side. It could be like A cross B, B cross A, whatever the letters are. But what you're going to do is the left vector, you're going to use your index finger, and the right vector, you're going to use your middle finger. And I need to show you what the hell I mean by that. So remember I told you guys, make your hand like this. So make your index and your middle finger perpendicular to one another, and then stick out your thumb as much as you can. So for example, here, I'm doing V cross W. So I'm gonna put my finger so that it points in the same direction, relatively in the same direction as V. And then put my middle finger so it goes in the direction of W. So is this cross product vector pointing in towards the board or out towards you? Out towards you, because that's what your thumb says. Okay. Versus if I had the vectors like this, in the other direction, now I would have to turn my fingers like that. So that V points in the direction of this, my mid index finger points in the direction of V, and this is like towards W. So now notice my thumb is going inwards. So now the orthogonal vector shoots inside.
You know that V and W are on the same plane, so the cross product is not the same.
How do you- You mean like this?
Yeah.
Then, well, because the vectors V and W are on the board, it goes like that. But like in general, if I had, let's say V was the green one, and W was the blue one, and it was like that. So I would put my finger and I go V cross W, and then my that tells me the orthogonal will be left. Versus if it was like this, like that, right? Or let's say it was like that. This is V, so then I would do V, W, and now the orthogonal vector just points this way.
So the cross product of V and W and the cross product of W and V.
That's one of the properties we're gonna see. Yeah, they're different, right? And they're different, but they're also kind of related in terms of like, if I go like this with my fingers, V and W points this way, but now if I swap these two, it's just pointing in the opposite direction.
Yeah, the result is like they have opposite dimension, but I
That's
guess
right.
their magnitude is the same.
That's gonna be a property that we're gonna learn, yeah. And we'll see how we know it's the same. Right? So in your notes, if you just wanna do a little sketch here. Let's say this is A, vector A, this is vector B. And then you have a cross product vector, A cross B. Versus, let's say A is also pointing here and B is also pointing here. But now I wish to do the cross product B cross A. I swap. Yep.
So it's kind of arbitrary, deciding which one is A and which one is B.
It depends which one's on the left and which one's on the right, yeah. That's what matters, when you're doing the cross product.
Like literally in the equation on the left.
Literally, visually, yeah, like whatever's here, whatever's here. This is the left vector, this is the right vector. Yeah, that's what I meant. So here, practice, guys. If I do A cross B and I do it this way with A pointing here and B pointing here, is this pointing outwards or inwards? Yeah. Which one is your index finger? A or B? A, the left one, right? The one on the left. So A, B, that way. So this one's going to point outwards. But now I still have A here and B here, but now I'm doing B cross A. So now my index finger should be the B vector. It feels a little uncomfortable. But yeah, so now it's this way. So notice it's pointing inward. Wow, this like muscle where those bones are. So now it'll be going inwards. Okay. That's gonna matter later because we're gonna look at surfaces, and you're either going to point up in one direction to the surface or below the surface. And that will matter in this case. Okay. The next comment I have are oh yeah. What I want you guys to notice, my other comment is the dot product is defined for vectors in any dimension. Any dimension. I can have a fifth dimensional vector, I just do V1 times W2 plus V2 W2 and so on, right? All the way to V5 W5. If I have any direct dimensional vectors, but for this is only going to be defined in 3D space and R3. Okay. So the cross product is only defined for vectors in R3. That's one thing to just be careful with. And the next few comments I have are linear algebra related. If you haven't taken linear algebra, don't worry. I'm gonna loosely define some things. So what we're gonna do is we use a tool from linear algebra to compute the cross product. To compute the cross product. And so in linear algebra, or even some of you guys that took pre-calculus, in some pre-calculus textbooks, they define something called a matrix. So in linear algebra, a matrix can be thought of as a larger vector. Okay. A vector is kind of one-dimensional, meaning it only has information going horizontally, okay, or vertically. There's only one strand of information. But matrix has multiple pieces of information. This is right here, what's called a 2x2 matrix, meaning there's going to be 2 rows of information and 2 columns of information. And so we can say this is A, B, C, D of information. A, B are in the first row, C, D are in the second row, AC is in the first column, BD is in the first column. Second column, sorry. So this is called a 2x2 matrix. And then there's bigger ones. This one we can call it a 3x3 matrix. There's 2x3, there's 5x7, there's all kinds of different dimensional versions of the matrix. We're going to focus only on the ones that have the same number of rows and the same number of columns, called a square matrix, because it's the same number of rows and the same number of columns. When you end up having more, a lot of different things to put in, you don't use different letters. What you do is you use the same letter, but you're going to give it 2 subscripts. Okay. The first subscript will talk about the row that you're in, and the second subscript will talk about the column that you're in. So for example, this one is in the first row, second column. And this one is in the first row, third column. And then you just keep doing that. This one here is in the second row, first column, second row, second column, second row, third column. And then the last one is, this is in the third row, first column, third row, second column, and then third row, third column. Like that. Okay? Just the way vectors have magnitude, right? There's a way to produce its length, its essence of how long that is. Matrices have a version of that. It's called the determinant. Okay? And so the determinant of a 2x2 matrix, what you do is kind of like absolute value of the matrix. You put 2 vertical bars like that. You put the entries of the matrix in here. And the way you find its determinant is you multiply these diagonal entries, so you do A times D minus these the product of these diagonal entries, B plus C. And then when you take linear algebra, you learn that determinants like are hella used in these objects, okay? They help you compute all these different things, and depending on what the entries are, if they're numbers, if they're functions, like all determinants give you all these cool things. But the one we're going to use is the determinant of a 2x2 matrix and the determinant of a 3x3 matrix. Of a 3x3 matrix. So that one, it is a lot of writing, I apologize. I'm going to rewrite this whole thing here, so I'll wait for you guys because it's going to take a while. 822, 823, 831, 832, and 833. Sorry for all that writing. We got this. So you do a product of these, mine is a product of these. When you'll learn in linear algebra, there's different ways. There's different process of different. You can take a different process for finding a determinant. The one we're going to use is I'm going to use my top row, and this is what's going to happen. I'm going to start with the first entry in the top row, and then what ends up happening is that entry. What you're going to do is you're going to remove from your site everything on the first column that contains that entry and everything in the row that contains this entry as well. And then you guys see how you have a smaller 2x2 matrix here now? You're going to multiply that entry by this smaller by the determinant of this smaller 2x2 matrix like that. Like that. And then you move on to the next entry, which is A12. And instead of adding, you're going to subtract that. 1, 2. And then with your eyes, you're going to do the same thing. You eliminate the column containing this entry and the row containing that entry. And then you use the ones that are left to produce the 2x2 matrix. So it's what I was having you guys do here. Remember that when I was going like this? It's that process that's happening. Okay. So I remove this, I remove this, so I'm left with, let me remove my green line here. So I'm left with these 4 right here. So it's A 2, 1, and 2, 3, 2, 1, and 2, 3, and A 3, 1, and 3, 3. And if you take linear algebra, you'll learn that you do this pattern of positive, negative, positive, negative, like that will continue the bigger the matrix is, okay? So the next one's positive. What's the next entry there? It's gonna be, yeah, so I did this one, so now we're gonna do A13. A13. And now I eliminate this column, I eliminate this row. So I'm left with these 4. A21, A22, A31, A32. So I'm not going to have you guys memorize. I mean, you could if you want. Memorize that formula for the definition. What we're going to do is we're going to use the determinant tool to help us compute the cross product. So we'll use the determinant tool to compute cross products. I'm only gonna show it this one time, step by step. After that, we're just kind of gonna do it the shorthand version, the shorthand way. So say we have vectors v1, v, with v1, v2, and v3. And w has w1, w2, w3. To compute the cross product, what you're gonna do is you're gonna create a 3x3 matrix. Where on the top, we're gonna put the standard base vectors, I, J, K. On the next row, we're gonna put the entries of the vector that's on the left, which in this case is V. So then I put V1, V2, V3. And on the last row, I put the vectors, the components of the vectors on the right, which is W, W1, W2, W3. And then you do this whole process here. Yeah.
I noticed that the top row is vectors, while everything else is scalars, right?
Correct. Yeah, these are vectors. So it's not exactly a determinant of an actual matrix because a matrix should contain entries that are the same thing. Yeah. So it's just kind of like a fake version of a determinant to help me produce the cross product. Yeah.
Okay, we see the first row is one.
Well, not yeah, but not quite because of this next step. So watch, when I take the determinant of this I hat is like the A11 right here. So we get I hat times the determinant that I get when crossing that column in this row. So it's V2, V3, W2, W3. And I get minus J hat. Cross off the middle column in the top row. And we're left with V1, V3, W1, W3, plus K hat. Yeah, so like in reality, we should put like quotes here for determinant because it's kind of like the determinant, but it's not actually the way. This is not an actual matrix of all of the same kind of things. Okay, erase this guy, erase this column. You end up with V1, V2, W1, W2. And the reason you don't want to put 1, 1, 1, 1, 1 here is because this, remember, we learned that we can write a vector as a sum of things in I, J, and K. By doing that, this is telling me that the result of this cross product says that the first component is really this determinant of this smaller matrix, because that's the one that's multiplied with I hat. So this tells me that this is really the vector where the first component is this matrix here, or the determinant of this matrix here. The middle component is because of the J hat, is the negative of this determinant. And then the K hat tells me that this is a third component. So practice that real quick. Here's V1, here's W. Redo this cross product, but I want you guys to do it in this manner, like this. So you can practice that, okay? So do the cross product of V and W, but you don't have to go all the way from here if you don't want to, okay? You can just go straight to here. Whichever one you feel how you're gonna start. Okay? Do it again. Just so you guys practice using that tool. With the entries that you're gonna plug in here. Hello, that's you. Yeah, that was a lot of me talking, so let me try it out. You have the answer here, hopefully you get this guy here. Say it again?
After having this measurement stuff, we just like to find out the.
Then you just go ahead and find the determinant through this process. Yes. Yes. Let's see, hopefully you're putting 3, 4, 1, 1, 1, 4, 1, 1, 3, 1. The middle one is what might look different from what we did here. But because of that negative, it turns out to give you the same results. Okay. So it's way more complicated than dot product, right? There's a lot more that you have to do. So what's going to happen is when we continue classes in the semester, whenever there's a step where we have to do the cross product, I will already have done it in my notes to save us time. So I'll just do the result in class, but on the notes, I do the actual work of the cross, just to save time. Okay. Not today because we're barely in it, but in the future class. Okay, so this is the cross product. We know one property that it produces a vector that's perpendicular to the other two. So I just want to show you guys some other properties that are going to be used in like proofs and other things that might come up in the homework. Definitely, this is one of them. This is one property. And a few other properties of cross products. These are a little bit more algebraic now. Questions on this here? You took linear algebra. Did you guys do this? Yeah. You did that, right? Okay. Hope you did. Okay. And if not, it's all good. Yeah.
You were saying on the right side of the board with like determinants?
I'm saying
Those are real.
this is how it's defined with a determinant. Yeah. Yeah, the reason I put quotes is because what we have here, like when the definition of a matrix, you want all of these things in here, all these entries to be the same thing. So either they're all real numbers or they're all like functions. Like you'll see there's all kinds of weird stuff, but you can't have different things in them. They should all be the same type of elements. And that's not what we have here. These are going to be real numbers, but these are, as I was mentioned, these are vectors. So that's kind of why I put that. You can ignore it. You got it? Okay, cool. Okay, guys. So I think the first property you guys already noticed. So let's pretend we have some vectors here. So for vectors v, w, u, and scalar c, if you're just adding the class, the textbook, when they say scalar, it means a real number. Scalar is a real number in this class. Okay. I'm thinking they call it scalar because it scales vectors, like it stretches them. And my own reasoning, I'm not really sure. But yes, so one of the properties that you guys already are noticing is that because of the right-hand rule, right? If I change these and I make W on this side and V on the other side, what did we notice about their directions? They're opposites of each other. Okay? And therefore, cross product is not commutative. I can't just swap them and get the same thing, like I did with dot product. The other useful property that is very similar to the dot product is when I have a scalar. If I scale V by some number C, if I stretch it and then I do the cross product of W, it's going to end up being that scalar stretching the cross product vector by the same amount. So if I double V, then what ends up happening, is or was that a hiccup? A hiccup, okay. What ends up happening is that new vector that you created gets stretched by that C. Or it results in also stretching W. So that C kind of intertwines with in this manner. And I think you guys on Tuesday said, so therefore, if I have C stretching V and I have C stretching W, what really happens on the outside of it? Like if I have this and I have this, what ends up happening to the cross product vector? That's right. The 2 pops out and the 3 pops out. So it's really a 6. Okay. Right? There's more. I'm just going to write the first 3 because they're the ones that we're going to use the most. But there are more. I'm not going to write all of them. VW. So this is about distribution. If I have 2 vectors adding and I do the cross product with V, it turns out with this whole complicated process, it turns out that it does distribute. If you work it out, it does give you the distribution. You do get V cross W plus V cross U. That's a good thing. That makes the math a little easier. And there's a few more in the text. But these are the 3 I definitely want to show you know when we're working out some of the problems, and maybe I'll do a proof on the board or something like that. Yep.
Number 2, they said like there are 2 times, and that equals 6.
It would be equal to 6 parentheses B plus W, right? Yeah. All right, guys. And so then look, another very important property is so important. It's a theorem. A little bit more of me talking, and then I'll have us work on some problems. Okay. It's similar to the dot product here. It has to do with the angle between them. So if theta is the angle between V and W, Remember, it has to be from 0 to pi. The angles we're only looking at are from 0 to pi. Then we get a similar type of result, but it's about their magnitude. Then the magnitude of the cross product is equal to the product of the magnitudes. And instead of cosine, this time it's going to be sine of theta. It's very similar looking theorem. Remember I showed you guys the proof of the other theorem of the dot product? We looked at that used like the law of cosines and all the stuff. The theorem of this is similar. It actually uses the theorem of the dot product. Okay. So it's pretty similar. And so the smaller the magnitude of the vectors, the smaller the magnitude of the cross. The proof is similar to the dot product, similar to the dot product theorem that we learned on Tuesday. All right, last property. One of the properties is going to talk about. One more, and then that's it. The properties that uses this theorem. So the last one has to do with the area of a parallelogram. See, I don't want to squish too much work on the board because it's too small. So I'm gonna do this. So consider some random vectors v and w. Okay, so let's say v is floating here in space, and w is floating here in space, and you put their ends together. Then what you're going to do is notice that there's like a parallelogram shape. If I put u here and if I put w here. Okay. If I put the v vector here and then I put the w vector here, it lines up so that I create this parallelogram shape. Okay. How did we find the area of a parallelogram? You guys remember? Similar to a rectangle. Length times. Well, for the rectangle, it's like length times width, right? And here, it's that width is really the height, right? So the area is going to be base times height. How long is the base? The magnitude of v. The height is what we don't know, right? It's not w, the height. So we're gonna have to figure out that height. So drop a nice little perpendicular so that we create a right triangle. There's some angle theta here. That theta is the theta mentioned in the theorem. It's the angle between v and w. And let's label this height h. So we know that the area is going to be the base times the height. Yeah. But we need to figure out what this h is. Let's do a little trigonometry. What trig function uses this side and the hypotenuse? Sine, right? So we have that sine of theta is equal to the length of h. And what's the length of the hypotenuse? The magnitude of w. So we solve for h. That tells me that h is just the magnitude of w times sine of theta. Oh. Okay. So we did like a little bit of side work. to find what H should be, it equals that. So now we go back to the area of the parallelogram. So the area is gonna be the base. How long is the base? Magnitude of V. And what did we just say the H was? Magnitude of W sine theta. And then if we use that theorem, what is this equal to? That's right. So then it turns out that when you get two vectors and you create this parallelogram, the way you find the area is you just take the magnitude of the cross product vector. So here's an application of the cross product. What would you do if you wanted to find the area of this blue triangle? Just get the area of the parallelogram and half it, right? So and then all kinds of other applications. Okay, time for you guys to have some fun. And then we'll take a break after our fun little activity here. Okay, with your group, I want you guys to try out this practice problem. The same groups that you had in the warm-up. Okay, so use vectors to find the area of the triangle with corners being these points. A having coordinates 1, 0, 0. B has coordinates 0, 1, 0. And then C has coordinates 0, 0, 1. So in 3D space, you have this triangle right here. Okay, here's A, 1, 0, 0, 0, 1, 0. Here's B, and then here's C. So I want you guys to use vectors to try to find the area of this bad boy. Actually, I'll leave this here. If you need to reference it. Is it okay if I have you go back? That I wasn't recording. Guys, remember these are points, not vectors. Okay, these are points, not vectors.
Yeah. So you see the piece like that, right? That's for example, you fly with that. but I mean, yeah, there goes points. So that gives you. Well, I guess it's like. It's depends on. You see. You can use this. Equal. Equal to the vector. You know, if you guys need some help, I'll walk around, help you out. Yep. This that we learned a long time ago, like one people back there, one second. Oh, yeah. Points. Where's I here? Okay, yeah. So this depends on the angle, but this does not. That one does not. Yeah. Well, the thing is, you don't need to find it. If you can create two vectors that kind of match what we were just saying.
No, I
Then
know how
you
to
take
do
a
it.
cross product,
I'm
take the magnitude, and that's what we
You do
reduce the
proper-
area of the parallelogram.
by
But then the triangle.
Yeah, exactly. Also, and I can see that. Yeah, it's pretty much.
You can use that, you can use that.
Yeah, Sean, if it's good, I'm pretty bad.
I'm going to give you like this one. Wait, what is it?
No, not, you're not saying the,
Yeah.
the actual vector.
Or like, this is your.
Oh, no.
So that if I write my vector v on the top and w on the bottom, I can quickly compute it by just like, instead of memorizing which one, is it v1, w2, or is it w2? I'm gonna be using the determinant to just say it's gonna be this minus that. And then the negative of this minus that. So you'll see me use it like that.
Like the base is now this point was the word and then I mean it's not like I'm not excited about the area of the parallels now.
Guys, just a reminder, we discussed last week that if I have 2 points, A and B, remember we figured out how to compute the vector using the coordinates here. You guys remember that? It was here, which one's the initial point if I write it in this manner? A, and then the terminal point B, right? So remember, to find the vector connecting A and B, it was x2 minus x1. And then it was y2 minus y1. This is from last week. And then z2 minus z1. That's what we learned to create a vector using points. Okay? Keep going.
I don't think it happened. Slides on.
In this case, that turned out great. But on the homework, for example, you might not even know like because that's collateral triangle.
Don't even think about it.
Like you could still do this. The area is what
Cross product. That's right. So like,
No.
in order to see the would we like to draw the imaginary line between the right triangle, the whatever is or and now you have two vectors.
That triangle is half of a parallel
Just
for a second, which is the perpendicular line. It's naturally parallel. It depends the two vectors that you.
Yeah, I know. It's literally.
Okay, so I'm doing it that way.
Where
You can do A, but I feel like at that point. Doing it.
Yeah, well, remember the height would be this length right here.
It's like, kind of like to document it.
So not thinking of it as just a triangle, trying to figure out the height range from B to C.
Yeah, because it's slanted, but what this triangle really looks like, it really looks like this. Yeah, so this C to B, for example, wouldn't be the actual height.
I think something, well, I mean, you said that like, right now.
I drew it like this. Maybe you can see it better. How can, what parallelogram can I draw?
Yeah, exactly.
You can.
CB, you said?
I.
CA and AB? Okay. And then the parallel, what would be the other half? The parallel. Correct. Yeah.
You can make your triangle.
So if you use this parallelogram, according to what we discussed here, what are the two vectors that you're gonna use?
Wait,
I find that easier.
You both wanted to start from here.
yeah.
And AC. You're gonna wanna use
Yeah, no, that's one.
this vector and then use this one.
1, 3, 3. 1, 2.
Does it matter which two vectors actually?
If you do CA, it, I think no in this case because you're using magnitude. But for example, if I decide to use CB and CA, like if I use these two, CAC and CB, I guess you're going to be looking at this parallel, which is still going to have the same area. Yeah, it's still going to have the same area.
As long as you start at the same point.
Yeah.
It doesn't matter, because what kind of a computer,
What case?
It's
Other times.
like this speed one, this speed.
Like, yeah.
This is-
Could you use any combination?
I think in this case you can use any combination because whichever two vectors you use correspond to a parallelogram. But
What case would it? Actually, let me make another vector.
yeah, I'm thinking of them having different lengths.
We just cross product.
I think in this case it won't because of the magnitude. Yeah, I think in this case it doesn't, in this particular example, because it's magnitude, so it doesn't matter. It'll either be like this property because of the direction. So you get the negative or you don't, but because it's magnitude, it gets rid of the negative. Yeah. All right, guys, we're gonna go on a break. Class, real quick, you can use different combination of vectors. Here are my solutions on the notes. I just use vectors AB and then AC that correspond to like a parallelogram of this shape. And so the area will be half of this using this formula here. So the area is a cross product of the two vectors kind of making up these sides of the parallelogram. So I created vectors AB, I created vectors AC, I did the cross product, all that work is here to give me the vector 1, 1, 1, 1. Took the magnitude, turns out to be √3 divided by 2, so the area is going to be √3 over 2. Okay, which I think in decimals is 0. Oh, I didn't write that. What'd you guys get? 866? Yes. Okay, sounds about right. Okay, let's take a break. Come back at 3:20, sorry, 2:26. Resume at 2:26. We're done with this section, okay? Oh, no, I wrote them the way the text is. I know. This because does the text do it this way? Let me see. Now I'm thinking it probably doesn't. All right, guys, we're gonna go back. Bring it back. Is anyone outside? By the way, who does anyone drive through the Cortinas Bridge to take Highway 4? I heard that this starting today, the Cortinas Bridge, like if you're coming from like Fairfield, when you're going down to 80, that bridge is gonna be closed. That road. Actually, no, the bridge, the bridge all the way to Hercules is gonna be closed starting tonight, all the way to Monday. So just prepare. The detour is go through Benicia, take the Benicia Bridge, take the 4, and then hit the 80. Just be careful, okay? If you're going to work or something, yeah. Just keep that in mind. That's on the video, so that's cool. That's gonna be a memory timestamp in the video. 2020. All right, guys. So we're done with cross product. We're finally gonna start looking at more graphic. You know, you guys have been really eager at graphing. So now what we're gonna do, we're done going over very vectory kind of part of the class. Now what we're gonna do is everything we've used with vectors, now we're gonna apply them to help us out with graphing and surfaces and lines and all this kind of stuff. Okay? So we're gonna start first with equations of lines. I'm splitting up this section. It covers equations of lines and it covers equations of planes. We're gonna do lines today, and the next time we're gonna do planes. When I was reading your guys' math autobiographies, you were wondering where you're going to use Calc 2 in the class. So far, I think you haven't used much Calc 2. Today, you're going to help use it, where it's parametric equation. Somewhat remember parametric equations? Okay, I'll remind you that as well. So we're going to do equations of lines in R3. Okay. Remember on day 1, when we were covering equations in R3, when you graph an equation in R3, what were the graphs? What dimension was that? When you're graphing them in R3, the graphs were 2-dimensional surfaces. But lines are 1-dimensional curves, right? So that's why it's a little more complicated for lines. You can't just find this equation. We're gonna have to use parametric equation to help with the line. Okay. So let's see. Let's construct this from scratch. So let's consider. Let me give you guys before I jump into this. Let me give you the gist. When you guys were in algebra, what were the 2 main things you needed for lines? You need a slope and you need the point. Okay? The point tells you where the line is at, and the slope tells you how it's slanted. Remember that? Okay. But now, but now if I have a line, I want to see how it's oriented, and I want to see the point where it's going to cross. Okay, so the point will still be used to tell me where the line's at, but now instead of just being slanted in one way like this, now I have depth as well. So we can't just use a slope. So what are we going to use to tell me the direction of the line? We're going to use vectors. Okay, So now instead of a slope, we're gonna use vectors to tell me which way the line's pointing. Okay, that's kind of the idea of all this. So let's see how we're gonna do that. So, we're gonna consider a line passing through 2 points. So consider the line passing. Right, okay. The line passing, through, let's call it P naught. Okay, so we'll call that P naught and P. These are the 2 points. Let me show you that they're gonna be. So let's say, the marker. Let's say P is floating in space somewhere in here. Sorry, P naught is floating in space in here. And P naught is gonna have coordinates X naught, Y naught, and Z. P, let's say it's floating somewhere in here. That one's just gonna call it X, Y, Z. And so we're gonna consider a line that passes right through those 2 points. Okay. So the point that we're going to pick, that I was showing you guys with that random piece of wood, is P naught. This point's gonna be fixed. This won't move. P is gonna think of it as a point that kind of varies through the line. It'll move through the line like that. But this guy will not. Okay? So we actually read it. So P naught is a fixed point on the line. P is here is a point on the line that varies. Varies. The P naught, we're going to do the okay. How do you think we're gonna have the vector that points in the same direction? How can we get a vector? Yeah, just use P naught and P, right? So we're gonna use this vector right here. And use this vector as our slope, the one that controls the orientation. We're gonna call that V. Okay. V is going to be the vector P naught. And this is where it gets fun. This is where the parameterization is going to get. We also have the position vectors that connect to those points like this. Then we have these position vectors. So we have this vector here that connects to P naught. That we're going to call that position vector R. And then we have the other position vector connecting to P. That one we'll just call R. So then R naught is the position vector X naught, Y naught, Z naught. Remember the notation for position vector is it starts at the origin and it has components of the point that it's terminating. The R is X. Okay. So we've constructed stuff, okay? We have things to play with now. What do you guys notice is the relationship between these three vectors? V, R naught, and R.
The R is like unknown.
This one, say it again.
So R is like unknown.
Are you unknown? Say that one more time.
Yeah, you, I mean, the vector R
Uh-huh.
equals the vector aspect.
Oh, gotcha. Yeah, that's right. So notice that if I add R naught plus V, we use you remember when we did vector addition? This vector plus this vector equals this vector. Okay? So notice that R is equal to the vector R naught plus the vector V. And that's true. That's going to be true no matter where I move the point P. If the point P was over here, then V just gets longer, but then R is still over here. Okay? So if I move the point P and I move it over here, what did I do to the vector B? Stressed it, right? And what if I moved it over here? Now what happens to the vector B? Shrunk it, right? So for me to move the points along the line, what can I do to the vector B itself? I can do a scalar multiplication of B so that it shrinks it or stretches it, and then therefore the point P is what's moving. Okay? So no matter where I move it, if I shrink B to here, then R will move here. And so it'll still be R naught plus the scalar multiple of V equals 5. Okay? So this tells me that this is also true if I do a scalar multiple of V. And we're going to use the letter T for that scalar. For some scalar T, which in this case is going to be our parameter. It's the thing that's going to be stretching and moving those points. Okay? So if we let this vector V here have components A, B, and C, we get R, which is this guy. We get that R. Here, let me write it again so that you guys can see it. We get that this is going to give me this. R is just, what was it again? X, Y, Z equals R naught, which is X naught, Y naught, Z naught. Plus the scalar multiple of V. What happens with this T here? What does T do to the components? No, it scales it, multiplies both. And because vector addition, I just add the components together. So this turns out to be X naught plus TA, Y naught plus TB, and Z naught plus TC. And so what ends up happening is we've parameterized the coordinates the points on the line have coordinates x, y, z, we have now found linear equations, linear functions for each coordinate. X is equal to this linear function, y is equal to this linear function, and z is equal to this linear. We've parameterized the coordinates on the line using the coordinates of this point and the components of vector v. And the components of vector v. So before I write the definition, let me just show you visually what's happening. Let me refresh my screen here. Hopefully it works. Okay. Okay, let me put this on Zoom so it shows it. Okay, so here's R3. Here's a point on it, floating in space. And this is the vector V that we're talking about. That's what's telling you how the line's oriented. And then this is the line that passes through that point that goes through, it goes in the direction of V, okay? U is this R right here. I wrote it differently. U is this R here. Okay? As I scale my vector V, that point moves. This point right here, P is moving. And so R moves with it. Okay? That's what's happening. And so when we're gonna parameterize curves in this class, I want you guys to, this is kind of silly. Who's ever watched the Disney Channel? Okay, do you guys remember when they used to say, you're watching the Disney Channel, and had a magic wand and sketched the Mickey Mouse head? That's kind of what we're gonna do in this class. We're gonna have an imaginary wand, and there's a vector that's the paintbrush. And the tip of the vector is going to paint the curve. That's how we're going to do curves in this class. This vector here paints, but in terms of the graph, the vector is invisible. The graph is the line itself. It's what the Mickey Mouse shape is. Okay? It's not the paint. That's kind of what's going to happen in this class with curves. Okay? So, say it again. Yeah. Yep. Yeah. Except that instead of being on paper, it's floating in space. Or like I guess now we have VR, right? Where you can put VR and there's 3D painting. You kind of get a brush and then you paint and then you walk away from it. But then whatever you drew is still there. That's what's happening. Yeah. Question. Yeah, that's right. Yep. The line is just the set of all the terminal points of this vector. Right. Yeah. But to describe how X is changing and how Y is changing and how Z are changing of that point, that's where we use these parametric equations. Okay. And so that's how we're going to define the equations of X. So the parametric equation of a so let's let L be a line passing through, let's say, the point that has coordinates x naught, y naught, z naught. That is parallel to the vector v. And this vector, we're always gonna have the components be labeled as A, B, C. So here's your point. X naught, Z naught. Now, I think I was discussing with your classmates over here. This vector v, remember, it doesn't have to be positioned here. It can be positioned somewhere else. Right, this vector v can be positioned over here. It's just the line has the same direction. But normally the textbook is gonna draw the vector so that it's right at that point. It's gonna draw it like this. Like that. But v can be wherever. Okay? And then therefore, the equation, this is L right here. This is the line. Okay? Then all points on the line are parameterized by the functions. So x is going to be parameterized by the variable t, which is this t here. Given by, you start by the x coordinate of the point plus t times the x component of the vector. And then so on. Y is parameterized by 1 naught plus tb. And z is parameterized by z naught plus tc. Okay. Let's go here. And this vector here is going to have a special name, okay? We're going to call this the direction vector. You can think of it as like the slope of the line. Questions? No? The vector is a slope, but you gotta be careful. Slope is a number. This is a vector. Okay? In R2 it can. In R2. Yeah, in R2 it can. Yep. So is that slope? Is that will show up later. Yeah, it'll still be related. Yeah, right now we're just dealing with straight lines. Later on, we're going to deal with curves. And then we're going to find a derivative at a point on the curve. And that derivative will be the tangent vector. So that will play on the derivative. Okay, let's take a look. Let's play with an example. You guys can see a concrete picture here. That's happening. Okay, let's see. So let's find the parametric equations of the line passing, let's say, passing the point 5, 1, 3. which is parallel to the vector 1, 2, 3. So that's what I say, 5, 1, 3, 5, 1, 3. And then the vector 1, 2, 3. Okay. So let's see. So this point here is like the x naught, y naught, z naught. Okay? This is the point, x naught, y naught, z naught. And the vector b, this is like the a, the b, and the c. So then, according to all the work we just did, the x is going to be parameterized by 5 plus t times 1. Okay? So it's x naught plus t times 1. The y coordinate is parameterized by 1 plus 3 times 2, sorry, t times 2. And then z is parameterized by 3. Oh, you gotta be careful. This 3 is because of the z naught plus the c, which comes from the vector. So think of t, the reason they use t is because you're thinking of it as time. Okay. Note. Think of it as time. At time 0, what point is on the line? Time 0. Plug in 0 to all these. Okay. 5, 1, 3, yeah, 5, 1, 3, which is just that point, right? That means that you start at that point. That's how you start pointing. And then as time is increasing, then that's going to give you direction as time is increasing. Okay? So this corresponds to the point 5, 1, 3. And then if t equals 1, let's say that's like 1 second, you plug in 1 to each of these. Now help me out here, what you get? 6, 3, 6. So now we're at the point 6, 3, 6. You do -1, then it moves back. So that's that drawing I was telling you. So you have your vector starting at 5, 1, 3, and then it moved within 1 second. Let's pretend it's 1 second. At 6, 3, 6. Question, yeah.
But maybe ask to convert from this form to like x, x plus like a.
That's
simultaneous equations.
yeah, that's a different type of equation, which is at the end. Yeah.
So it's kind of saying like, when the vector expands, what is the end of it?
Correct. Yeah. So that vector, the terminal point of that vector at time 0 is this point.
Because
It hasn't been scaled yet. Yeah. And then in 1 second, it has been scaled so that it's at this point. Yeah.
T is like time, but T can be negative.
T can be negative. Yeah. Yep. T can be negative. So here. Here's the problem. So here's the point. So here's, as you can see, this is now where like GeoGebra is going to start helping us out. So here's a point A that has these coordinates. Okay. Here's the vector 1, 2, 3. Notice that it's not on it, but it's still giving me the orientation of the line. Okay. And oh God, how do you parameterize? Let me see. I think you put curve Let me see, it's three-dimensional, so it's going to be this one. Okay, yeah, so it's curve. So we put the first function, which was, what was it? 5 plus t. And then 1 plus 2t. 3 plus 3t. And then I think I have to tell it to be, the parameter is the variable t, and it goes from, let's say, -5 to 5. There you go. So I'll have to code it on GeoGebra, okay? So I put, let me just show you guys. You put the function for x, the function for y, oops. The function for x, the function for y, the function for z, and then you say, I'm using t as a parameter, and have it range from -5 to 5. So then it'll go like that. Notice that the line is parallel to that vector. You see that? Okay. It starts off, it doesn't show you the wand. It doesn't show you the vector that's drawing the line. Okay. There's a vector that's going here. That was that R vector that's not being used here. And then after 1 second, it moves to the point 6, 3, 6, which is again on the line. Notice that it is indeed on the line. Right there. Okay. So it goes like this, and then with 1 second, it's stretched to now then go like that. Okay. I wanted to show you that. It's always nice to confirm everything. All right. All right, so what I want you guys to do, this practice problem here. So use, oh, no. You know what I want you guys to do? Put your brains together here. You can group. You're going to do this a lot in this class, so we're working on the group. So, show that if a line passes through P naught heading coordinates x naught, y naught, and z naught, and okay. We'll skip this part. We'll be on the next. I really want to cover the next part. It's hard. It's harder. Okay. Skip. Skip. Look at the notes. Sorry. Look at these. The next part's it's harder. So I want to focus on that since we only have 15 minutes. It's harder. Sorry. I know you guys are eager. I still have a practice problem. Yes, but this is harder here. Hold on, give me a second. Oh, that's right. That's right. Okay. Okay. No. Okay. Sorry. I'll get back. I'll bring this up later. It has to do with parameterizing a line segment. Okay. But I want to focus on this next part more. Okay. Say I have two lines in R2, right? In terms of the direction of the lines, what did you guys learn in terms of parallel lines? Yeah, so if two lines are not parallel, what happens? What happens? Intersect. Okay. What about an R3 though? Let me have you think about that while I erase this here. Chat about. Let me have you guys think about it.
It could be like.
I thought it would have to be like here, like. My dad. Not be. It's not. You got this, they're not this line, and this line, and they're still gonna like. But then there, they're like not reading the same direction. They're never gonna. Two dimensions. They can be.
Okay, let me see. Let me show you this. All right, let's see. So here are two lines that are they parallel? Definitely not. But they will also not intersect. Okay? Say it again. That's right. Yep. Yep. It's like two roads. They don't go in the same direction, but they also are not going to cross. So that property that you guys learned about parallel lines is only true in 2 dimensions. Okay? In 3 dimensions, that's not going to be necessarily true. So there's a new name for this situation called the lines are skew. The lines are going to be called skew lines. So let me write that down. They're skew. So in R2, if two lines are parallel, they must cross. This, if they're not parallel, two lines are not parallel, they must cross. This isn't true in R3. And so we're gonna define that. We're gonna say two lines are skew if they're not parallel and they don't intersect. And so I want to make sure that you guys know how to do all that because it's a short definition in English, but it's a lot of work in math. Okay. So you'll have a problem with this. It'll say determine if the lines are parallel, skew, or intersect. Those are the, in this case, those are the 3 situations that happen. And then they give you the equations of the lines. Let's name them. Let's say this is the equation for line 1. X, a t, y of t, z of t. Here, x is the function 1 plus t. Y is the function at minus 2 plus 3t. And then 4 minus t. And then equation 2 here's what you have to be very careful on, okay? If you are dealing with a different line, don't use the same parameter. Use a different letter. You'll see why later on. Okay, don't use the same parameter, use a different letter. What letter do you guys want to use? Let's not use Z because Z's here.
And.
I'm gonna use S. The textbook I think uses S. So let's go with that. I like N2 though. N's pretty good. I'll do N, but we know. All right, let's do N.
Too many choices.
Too many.
Damn.
That's a good point. That's a good point. I'm gonna go to vector S. Sorry, yeah, because N here is used for normal vectors and stuff that we're gonna do later. Let's go with that. Sorry, I know, I like N too, but that's right. Okay, this one is a different function. It's just gonna be 2 times S, 3 plus S, and -3 plus 4S. Why do you want to do that? Is because I want you guys to think of it as time. So as this time's moving, there's a point on the line moving, right? But t equaling 1 second won't be the same thing as s equaling 1 second. They're going at different times. So I mean, that's why when you guys see the different parameters. Okay, so first thing is let's see if they're parallel, right? This is a line going one way, this is a line possibly going in the same direction. So how the heck can I tell if they're going to be parallel since I don't have slopes? Well, when you guys did it in R2, what did you use to determine if the 2 lines were parallel? The slopes, right? But what's our new type of slope? Is that what you're going to say? The direction vector. That's right. So we need to figure out what's their slope. What is their direction vector? Right. Go back to the definition of equation. And notice that the coefficient of t gives you the ABC. Right. The coefficient of t gives you the ABC. So this tells you that this has direction vector. Let's call it V1 with components what? 1, 3, 1. Right, so that is because of the coefficients of t or of the parameter. Here, the coefficients of the parameter, I'm going to call that V2. These are direction vectors. Are going to be what? 2, 1, 4. 2, 1, 4. So now I want to see if they're parallel. The lines are parallel if what? If the vectors are not equal. The lines are parallel, meaning the direction of the lines are parallel. If the vectors are scalar multiples of each other, because you want the vectors to be parallel. If the vectors are parallel, the lines have to be parallel since they follow the same direction, right? Okay, so what we need to do is we need to see if the vectors are parallel. Therefore, we need to see if they're scalar multiples of each other. So we're getting now to a point where like things are building up, right? It's either the fun part or the scary part, depending on your perspective. Okay. So we want to see, are these guys parallel? So are they parallel? So I want to see if they're scalar multiples of each other. That's how we learn to determine the vectors are parallel. How did we do that? How was I having you guys do that last class? To check if there were scalar multiples of each other.
Just V1 divided by V2. No. Like, exponent by 1 divided by 2 equals 3 divided by.
That's right. You wanted to see if the components were proportional, if they had the same ratio, right? So that's what we're going to do. We're going to divide the x component with this x component and see is it equal to the y component divided by this y component? Nope, and it's not even equal to the other one as well. So no, not parallel. If this was like a 6, and this was a -2, then I would have gotten 1/2 equals 1/2 equals 1. And so yes, they would have been parallel, and then you're done with the problem. You would say the lines are parallel. So they're not parallel. And by definition, what do I want to check to see if they're skewed? I don't want them to intersect. That's where it's going to get algebraically heavy. Okay, how the heck do I check if they don't intersect? So intersect. Don't hate me, guys. I'm gonna go a little bit over, okay? But if you have to go, that's fine. No hard feelings if you have to leave. So to intersect, what can you tell me about this x coordinate and this x coordinate if they intersect? They're gonna be the same x coordinates, the same y coordinates, and the same z coordinates, because that's a point where they all agree on those coordinates, right? So if they intersect, we want to check. We want to check if x of t will equal y x of s, y of t will equal y of s, and z of t will equal z of s.
One of those
You're gonna need to see. We're gonna need to find the t's and the s's so that when you plug them in into each of them, they'll agree. If one of them doesn't agree, then they don't intersect. But it's kind of for some t and s. And here's where it really is important that you use different parameters. So x of t is 1 plus t, and then x of s is 2s. Then I got -2 plus 3t is 3 plus s, and then 4 minus t is equal -3 plus 4s. I'm going to save a little bit of work, okay? I'm going to call this equation 1 and equation 2 and equation 3 because we ended up with a system of equations. So using, this part just because I ran out of time, but it's on the work here on the notes. Using 1 and 2, we find that t will equal 11/5 and s will equal 8/5. So if I do elimination and all that good stuff, we end up with t equaling 1/5 and s equaling 8/5. Okay, that's shown here in the note. But I'm just running it. So then what you do is you say, okay, well, if this t and this s agree with these two equations, plug them into the third equation. And if they don't agree, then they don't intersect. If they do agree, then they do intersect. And then you use that to find the coordinates. So, so plug that in here. Notice for 3, if I plug in 11/5 for t, did I do it? Yeah. Right. What's that? 4 minus 11/5, and then 3 plus -3 plus 4 times 8/5. What's 4 minus 11/5? Is that 20 minus 11? Right? So is that 9? 9/5. This is -3 plus 20/5. 32/5. Help me out here. What is that? Not 9. 17 fits? Okay, not equal. So these two don't agree with this one, so they don't intersect. So this tells you that do not intersect, and so therefore all this work tells you that the lines are going to be lines are skewed. Okay? I didn't want to leave that not on the notes because that's really important. All right, 3 minutes over. I'm so sorry, guys. Now I want to do something effective.